With that, I'd like to introduce our next speaker to talk about another very prevalent topic, obviously brackish water. Stephen Hoff of the Bexar County Information Technology is going to be talking to us about brackish desal beyond the bad water line. Let's welcome him this morning.
Okay, so thank you very all for listening to me today, and special thanks to Mr. Jim Polanis for graciously inviting me to speak. Unfortunately, my thesis advisor and co-author, Dr. Alan Dutton, couldn't be here, so I'm going to try and carry the torch as best as I can. And given the short time frame of this presentation, I'm going to necessarily have to omit a lot of detail. But that being said, I highly encourage you all, if you're interested in what you see here today, to check out our paper of the same name, which is due to be published in the GCAGS journal this coming November. So, without further ado, the Edwards Aquifer, over the entirety of the Edwards group, specifically its brackish water and saline water zones, which will be the focus of this talk. But before getting into that, I'm sure most of you are familiar with the Edwards, but I just wanted to do a very quick recap and add a few salient points that might perhaps be less well known. So, the Balcones Fault Zone section of the Edwards Aquifer stretches approximately from the Rio Grande River in the west along the Balcones Escarpment all the way to the Colorado River in the east. This dark green section here is the Edwards outcrop. The light green area is the confined freshwater portion of the aquifer, and its down dip edge, also known as the bag water line, defines the limit of potable water and marks the 1,000 milligram per liter isopleth of total dissolved solids, or TDS, content. Now, beyond the bag water line, there lies a brackish water zone, defined as 1,000 to 10,000 milligrams per liter. And that can be seen with these contours right here. Now, the boundaries of the brackish water zone were established in the early 90s by Alvin Schultz, who took the deep resistivity reading from well logs in the area and converted that to TDS. And even beyond the brackish water zone, the Edwards group extends gulfward towards the Stewart City Reef trend shown here, which defines the shelf edge margin of the carbonate platform on which the Edwards was deposited. One other point that I want to make is that the Edwards hosts oil and gas reserves, fields of which are shown in orange here. And most of the production occurred from the 50s through the 70s, but to our knowledge, production is still occurring today, particularly in the Stewart City Reef trend for natural gas. So here's a very simple cross-section of the Edwards from the Balcones Fault Zone down to the Stewart City. The Edwards is part of this wedge of carbonates right here. And there's two things I want to point out specifically that weren't shown on the plan view map. One is the presence of these Atascosa and Carnes troughs, which are grabens that are thought to have resulted from the deformation of underlying Jurassic halite right here. And then, shame on me, these aren't labeled, but these faults right here are listric growth faults in the overlying Cenozoic section beyond the ancestral Cretaceous shelf margin. And these faults are known to be characterized by and trap geopressure, which will become important later in our story. So, one other thing I forgot to mention is that the pumping of fresh water in the That's better. The pumping of fresh water in the Edwards Aquifer is regulated by the state. Now, to our knowledge, correct me if I'm wrong, that's not the case with a lot of the brackish water in the Edwards. So now that brackish water is becoming a more popular, unconventional water resource, we really wanted to look at the brackish zone and see specifically what hydrogeologic and geochemical controls were affecting the movement and currents of brackish water. So how are we going to do this? Well, first and foremost, we would make two maps. One, a TDS, or salinity distribution map across the saline zone, and a hydraulic head map across the same area. Now, a lot of really good investigators have done some good research on the Edwards saline zone, and in particular, looking at the composition and origin of Edwards brines. But to our knowledge, no one has yet, in a systematic way, mapped out the distribution of salinity across the saline zone and then related that to flow paths that one would predict by looking at a hydraulic head map. And from this hydraulic head map, we want to look at the gradients and see what might be driving these deep subsurface fluids. And then we want to see if our maps are consistent with what Dr. Dutton and others might call the convergent flow hypothesis of the origin of brackish water, which I'll explain in a bit. So we have two types of data, very simply. We have TDS data and we have hydraulic head data. And these generally came from two different industries: the groundwater industry, which, as you can imagine, is very plentiful in the freshwater zone, and then we have the oil and gas industry, which is very plentiful in the saline water zone. And we can very nicely interpolate between these two data sets. So our TDS data comes from 5 sources. We didn't look at the freshwater zone very closely, but we did take nearly 1,500 chemical composition samples from the Texas Water Development Board's database. Another thing I should mention is that there's been historical concern about freshwater drawdown in the aquifer inducing the migration of brackish water into the freshwater zone. As such, there was a series of transective monitoring wells installed across the Bagwater line, so we took advantage of that data. Third, we took 129 samples from oil and gas wells from the USGS Produced Waters database. We also incorporated the results from Schultz's study that I mentioned earlier, and then we took Schultz's methods and applied them to some of our own wells we found in the saline zone. So here's our first map of salinity distribution across the entirety of the Edwards. So I know it's very busy, but I'll unpack it as best as I can. So as I said, we have the dark green outcrop, we have the light green freshwater confined section. The brackish water section of 1,000 to 10,000 milligrams per liter is shown in this pink. The open circles here are water samples from the transect zone wells, which are found along the Bagwater line. The closed red circles are samples from our oil and gas wells, and our crosses, or pluses if you will, are the results from Schultz's study that we incorporated, and they're mostly found around the brackish water zone here. And then finally, these X's are results from, or TDS estimates from our study. And what we've done is we've taken these data and we've interpolated these TDS contours across the saline zone. And there's a few things I want to point out. First, we have these very high plumes or bubbles of TDS around the Carnes and Atascosa troughs. We're talking TDS in excess of 200,000 milligrams per liter. So that's pretty salty. For reference, seawater is 35,000 milligrams per liter. A lot of earlier geologists studying these oil and gas fields along the troughs suggested that there was a lot of fault-controlled vertical movement of fluid originating from a deeper horizon, and that was one of the major pathways for hydrocarbon migration into the Edwards, and I think our map very well corroborates that. Another thing I want to point out is that likewise along the Stuart City Reef trend, we have very high salinity as well in the southwestern extremity in excess of 300,000 TDS, 300,000 milligrams per liter. So hydraulic head data came from 3 different sources. One, we took freshwater equipotentials or contours from a Edwards Aquifer Authority synoptic water level map for 2004, December 2004, which represented a period of high stand water levels in the aquifer. Second, we incorporated the data from transect wells. And then third and finally, we took pressure data from oil and gas wells from the Lasser production database. And these data came to us in either a wellhead pressure or a bottom hole pressure. And when we had wellhead pressure, we converted that to a bottom hole pressure, making certain assumptions about the conditions in the borehole. And with that bottom hole pressure, we converted to an equivalent fluid pressure at the bottom of the borehole. And then we could plug that into our standard equation for hydraulic head. gravitational potential plus pressure head, which is the pressure of the fluid divided by the specific weight. Now, one of the big questions we had to ask ourselves is, what density of water should we use? Well, we ended up going two routes and making two maps. So one was just a freshwater, equivalent freshwater head map using a uniform density of 1,000 kilograms per cubic meter. And another one, the saltwater point head map, we call it. We used a variable density interpolated from the TDS map. So specifically what we did was we rasterized the TDS surface from our contours and our control points, and then using the resulting TDS at each mapped hydraulic head well location, we converted that to an equivalent density using an empirical relationship we found from the USGS data. So here's our first head map. This is the saltwater map calculated using the variable densities interpolated from our TDS map. And much like the TDS map, our X's are the transect zone wells across the backwater line. These pluses are hydraulic head from oil and gas wells with their values given in meters. And then the blue lines are the equipotentials for the freshwater zone that we borrowed from the EAA synoptic water level map. And then, of course, these red lines are equipotentials that we interpreted. Now, a few things to point out. First and foremost, we have heads along the Stuart City Reef trend in excess of 1 to 2,000 meters above sea level. So theoretically, according to these data, if you were to put a standpipe in the Stuart City Reef trend, you would have water rising many hundreds of meters above ground surface. Now, another thing to point out is that we have very low heads around the Carnes and Atascosa troughs with an inward or inland directed gradient from the Stuart City Reef trend that we would describe with a negative sign because the direction of flow is actually opposite that from the freshwater zone. So here we see a reversal in head gradient and a minimum in hydraulic head. Much is the same with our freshwater map, which shows higher heads in general, and it actually shifts the position of this hydraulic head minimum and reversal and gradient further upwards, farther into the brackish water zone. But both maps tell the very same story overall. One, that a reversal in head gradient exists around the brackish water zone or the up-dip limit of the saline water zone. And there's very high heads along the Stuart City Reef trend. These heads are much higher than we would expect from hydrostatic fluid column stretching from the saline zone all the way to the outcrop. So what's causing these anomalously high heads? Well, long story short, we think the best explanation is geopressure, specifically propagating from the Cenozoic section overlying the Edwards. Now, these four frames are results from a variable density model that looked at the history of pressure evolution in the Gulf of Mexico Basin for the last 30 million years. And what you can see is this bubble of geopressure actually propagates from the Cenozoic section into the Edwards as shown in this green sliver here. And so finally, this cross-sectional diagram, I think, brings together our thinking fairly elegantly and simply. Essentially, what our maps are telling us is that we have two major flow systems. One is a meteoric shallow flow system with water moving down dip by gravitational drive, and another flow system moving up dip driven by ancient geopressure, sub-geopressure propagated from the Cenozoic section. And we posit that the brackish water zone exists and occurs as the convergence or transient and hydrodynamic mixing between these two flow systems. So there's a lot to unpack here. There's a lot of implications. But I really appreciate you all listening to me, and that's my presentation. So thank you very much.